So I'm going to start us off with talking about some of the things our customers are doing, maybe starting by how we got to where we are today and where we're headed. And I'll be talking primarily about storage systems that we're deploying for our customers. So just to talk a little bit about how we got here, I think AI and ML, certainly big data, it's really all about the data. And if you are a fan of science history, you maybe recognize Tycho Brahe here. Maybe you know Johannes Kepler a little bit better. But Tycho Brahe was a Danish guy that thought the sun revolved around the earth. And one of the key things that he contributed to science was data. He did years and years of observation, and Johannes Kepler was able to use the excellent data that he stored and was able to determine that, in fact, his colleague and his mentor was wrong, and that the sun, in fact, the earth, in fact, revolves around the sun. But I think it's a good story that talks about how we love to explore and explain things. And this all started from the very beginning when we were observing the world around us. And we collected data in a very informal way. And Tycho Brahe was probably the most notable first person that was very careful about collecting his data, keeping it in a way that other people could use it, and then making intelligent use of the data. And obviously mathematics with people like Newton came along, and amazing results we got from that. And so we've kind of had this ongoing cycle of going around, collecting more data, figuring out what to do with it. And it's helped us prove and disprove theories, and we're spending billions of dollars, sending particles flying around, collecting data and learning all kinds of things. And so we keep going on with this. And obviously about 40, 50 years ago, computers allowed us to start doing mathematical simulation, amazing outcomes. You have a Rayleigh stability there on the page as well. I'm a fluid dynamics person, so HPC fluid simulations were part of my upbringing. But I think the really interesting thing about that world is that you create huge amounts of data, but it's fake data in a sense. It's simulation data. So if you have a bad day and you lose your data, you can run your simulation again. Now, it might take 6 months, but you can run your simulation. But what we've got today is people collecting huge amounts of data. And it's funny because in a sense, we're starting to study the data more than we sometimes study the real world. So I think the important thing from a storage perspective is we've gone from Tycho Brahe's really cool notebook that he kept to petabytes of data. And there's a really common thread through all of AI and ML and big data analytics is that there's lots of data. And all kinds of things people have said about the new gold, et cetera. But the idea is that the common knowledge is, and the common thinking is, the more data that I have, the more I can learn. And so you've got these funky names for the careers. You've got data miners, data scientists. My favorite is data czars. But you've got all these people that are curators, in fact, of data, that take care of data. And I would say that one of the things that we've seen from our customer base is when people move into studying their data, learning from it, creating AI models from their data, they end up very quickly managing more data than they've ever managed before. A number of our customers have told us, this is my first multi-petabyte platform. This is the first time I've ever managed so much data in one place. And I think, you go back to this idea of Tycho Brahe's notebook. I mean, man, if you lost that notebook, he spent an entire career making observations, doing measurements. If he'd lost that notebook, it was a lifetime of work that had been lost. And I think that's one of the notable things that we're seeing from a lot of our customers is a lot of the data that they're collecting may not be invaluable, but it's certainly irreplaceable. You can't replace a lot of this data. And I'll go through some of these examples. Very often there's once in a lifetime or once in a year or once in a blue moon kind of events that if you lose that event from your data set, there's nothing you can do about it. So I think the importance of keeping your data safe, and and sometimes you don't know up front what the safe data is, but in any case, it's very important that this new kind of data compared to simulation data is very often irreplaceable. And I think the other piece that's really we'll see coming up over and over is, if you don't know what you've got and how it's organized and where to find what you're looking for in your data, it just becomes a swamp and you can't do anything with it. And I think, Tycho Brahe's notebook, you clearly see from this illustration that he very carefully laid all this stuff out. And I think that's one of the key things. So some of the things we've seen, I think I'll start with an example from the travel industry. Now, that was in a former time, people traveled all over the world and organized trips, and maybe that will come to us again. But if you think about it, how much data is being generated in the travel agents industry? As a matter of fact, one of our customers generating a petabyte of logs of requests a day. So you can basically, their idea was, we have a week-long FIFO of data. What we'd like to do is look through this data. They had to get rid of things like duplicates, because Kayak maybe asked 20 sites that asked them if a certain flight is available. But the idea was, okay, we have all this data. What if we could predict where people are going to be going a few months from now? What if we could tell people, predict the future, predict where are going to be the hot travel spots 6 years from now, do correlation with weather patterns, with world events, and be able to do predictions like you do weather predictions, but based on human behaviors. So the question was, what's truly meaningful in the data set? Obviously, it's very time sensitive, but the problem that they had was they were generating a petabyte of information every day, and they had to, there were probably really special, interesting things in there, but they didn't know what. And so one of the things that we worked together with them was to be able to manage to keep about 2 weeks of data on their platform, shrink down as a classic problem in this space, the really key events that they needed to keep for a long time, but manage a petabyte of ingested data every day. So that was the first example. And the idea in this space is to be able to use knowledge to not predict the future of airline routes, but also tell airline companies where they're messing up, what they're losing, and learning all kinds of interesting things, really having an intelligence associated with data. Another one from the automobile industry, I think, self-driving cars is kind of the poster child of AI and machine learning. Really buzzy space. Everyone's talking about it, all kinds of self-driving algorithms. And there's a lot of that going on. But I think there's a lot going on in this industry that's been going on actually for quite a long time. And things like lane minders that keep your car in the right lane, collision avoidance features that are on cars. All these things collect data from sensors. And the algorithms in the cars are doing intelligent things, doing driver assist all day long. Obviously, ABS and route guidance systems have been developed. But what about the event when something goes wrong and the AI in the car does the wrong thing? And those are rare but very, very important events. And what our automobile industry customers are doing is collecting that sensor data from cars and finding those bad day events when their algorithms didn't work right, and then going back to improve their algorithms, correct the errors. And the other piece is, okay, we've come up with this really clever new algorithm. We run it through 1 million miles of car driving and determine if really the result is better or worse, and do we create new disastrous events. And so you think about all this data coming in, it only really makes sense if it's real world data. And so they've spent years building up this real world data, and they continue to bring it in. And we're talking about 20, 30 petabytes of data that's used on a day-to-day basis to improve collision avoidance algorithms to avoid regressions. And I think this whole idea of documenting the cases that are really special, that's probably the same, my understanding is it's the same thing in speech to text algorithms, where you're really interested in when you're making mistakes, noting those events, storing them away, and then having your algorithms come back and figure out what they did wrong. So another example. I think digital pathology is a really interesting one. It's really an exciting topic. I mean, you can just go wild with this and about the things that you could do with digital pathology. You have today, you have a wet slide, piece of glass on which a tissue sample is placed. They're very reliable. They're very durable. They don't take any energy. Those are all good things. But what if you had digital images of those electron microscope images that you can do AI and ML with? I mean, there's so many things that you could do with this. For instance, you have algorithms determining if there's pathologies. You have algorithms determining if there's, maybe this is a pathological situation, maybe not. We pass this one on to a pathologist, and he or she can determine, is that a true problem? And then another amazing thing that I learned was that pathologists are trained. They ship boxes of these glass slides around the world with known anomalies, and pathologists learn from those sets. What if that was all online? The reason it isn't today is it costs too much money. It costs too much money to store these digital images. It's actually more economical to keep these boxes full of glass slides. So there's all kinds of things that you can think about doing it. Special inferencing, keeping your pathologists working on the most difficult cases. And there's really cool things that are being studied about this, having image banks that are created of very unusual pathologies to help people determine problems. And these special inferencing cases, one of the really cool things that's being talked about is using space-filling curves to name and store all the objects in an object storage. So rather than having this giant 3D model in a traditional file system and doing all these seeks in a file system, you can have little panes of your image stored in a very modern object storage. And you can find the part of the image you're looking for deterministically by the name of a space-filling curve. So there's really cool things going on there. And again, there's these similar needs we're seeing everywhere. The need to identify and tag really key, important images, keep those safe, keep other images that may or may not be interesting in the future, and then keeping the whole thing economically viable, because unless the price of storage comes down a little bit, digital pathology is just going to stay a good idea. I think banking is another example. Banking regulations are always evolving. Banks are getting in big trouble all over the world for tax evasion, money laundering. Really great example was the Panama Papers. If you read anything about this, some journalists actually digitized OCR, kind of traditional stuff, millions of documents, and did all kinds of cross correlations and determined patterns in the data, and were able to determine, there's fraud going on here. And as a matter of fact, you've probably heard the story, but eBay was unsuccessful until they used big data analytics to determine where the fraud was coming from. And again, I think this is a great example of a space where correlation of massive data sets is really difficult, and predicting what kinds of behaviors people are coming up with. There's no lack of creativity in this space. And again, we have an example with one of our banking customers collecting 400 terabytes of logs every day, and needing to keep that data for a year to do determination of what's going on and find strange events that can make for intelligent decisions. And then probably one of the other really buzzy ones of the day is genomics, and we're working more and more in the genomics space. And I think genomics is an interesting space because it's it's amazing data sets, and the human genome is amazingly capable of storing huge amounts of data. They say that one genomic sequence represents a couple hundred gigabytes of data. And there's so much to be learned from this data. And we're doing all kinds of correlation and AI work and trying to determine what characteristics produce what diseases. Obviously right now, in this period, vaccines, all these things, really important to determine what are the populations at risk. The possibilities are endless for this whole thing. And in a sense, genomics is a space where it's all about the data.
A lot of the challenges with AI are that the size of the data, the images, and that sort of stuff are small files, and a typical object storage is much more bandwidth oriented than IOPS oriented.
Right.
How does Scality deal with the small file access modes kind of thing that AI is driving?
Small files are definitely something of a challenge. We have systems that have several hundred billion files on a platform, so we're not really scared of small files. But I think the space filling curves was a really interesting example where instead of storing one giant image, they're storing layered images that allow you to move quickly between objects. Obviously, there's I/O patterns there. And I think some of the AI work that requires very low latency, very, very rapid access is not a good fit for object storage. And we're working with companies that are doing acceleration on really small IOs. So there's spaces that this all makes sense, and there's spaces that doesn't. We have partners, and I think Paul will talk a little bit about that, about how you work together with indexing on really fast storage, big blobs, if you like, on object storage. But we can go a lot further down in the small space than a lot of people think we can.
Mm-hmm. Yeah, and I think it's good to add to what you said, but to add some numbers. So if small is kilobytes, that's fine. With an object store like ours, it's not going to be a concern with kilobytes of size object. If it's below and it's like 100 bytes, 10 bytes, 15 bytes, we think of them as records more than objects. In that case, the best practice is to put all these records in a single file and have a bigger file with multiple records. Or you're going to use another solution to do that first layer of access. And I think that's something that Paul will talk about more.
One of the things that we've seen in this genomic space that I think is very interesting is that you have these libraries, in a sense, of genome sequences, and many different countries today are trying to collect libraries of genome sequences of certain populations in their country, but all kinds of issues around how can you share those with other people, how do you make them anonymous, what can you share with other people. And we're looking for, well, a lot of the researchers in this space are trying to figure out some sort of lambda functions that, rather than just asking for one of these 200 gigabyte files, you can ask the question, how about this particular characteristic? So it's not a SQL query, it would be more like a gene query, and maybe someday there'll be a gene query language that comes up. But do you have files with these particular characteristics? And there's a lot of work going on, and I'm not the expert in this space, being able to tag certain characteristics so that you can pull out 100 files with these taggable characteristics. And in Giorgio's example, he will show some ways that AI and ML are being able to define with a very few parameters some really interesting characteristics about things. So I think this is a space we're really expecting to see some progress, where your storage isn't just dumb, it isn't just blobs, but you can actually make a really sophisticated query to your pool of storage. And that's actually what some of the gene researchers that we're working with are trying to do, is have their gene library accessible via really sophisticated queries. So, and as a matter of fact, in Europe, we have the GAIA-X Health Data Hub, which is being created across Europe, being able to figure out how you can safely reliably share genome information between multiple data sets in multiple countries. And we're working on that with a number of companies.
You talk about this Europe-wide project, GAIA-X. I was just wondering, like, what does Scality have in place for governance of data? What, how can, is there anything in your product that can help with GDPR adherence?
So I think that's one of the really high potential functionalities of an object store, is that you can metadata tag. And I think one of the really big challenges of something like GDPR is that you need to think upfront about what you want to know about your data. Tagging a piece of data with its original owner, for instance, tagging a piece of data with its country of origin. If you don't do those kinds of things, it's very hard for us to help. But if you have some discipline about doing those kind of things, we can be extremely helpful. Being able to delete, for instance, find all the files belonging to a specific user and delete them. And that's probably the biggest challenge of GDPR, is the requirement to forget, to be able to delete data sets. It has been agreed with GDPR that data that's stored on things like magnetic tape doesn't actually have, you don't have to compact the tapes. You can just deleting the references is considered sufficient, which was good news for people with hundreds of petabytes of tape.
I was going to chime in. One other capability that we do provide sort of at the baseline level is we understand the location of the data. So we are able to manage a global namespace, and you can, for example, tag a bucket and say, this bucket lives in geography 1, another bucket lives in geography 2. We then take care that if you're storing the data in that bucket, it always resides in that specific location. Mm-hmm. That can be an on-premise system. It can even be a public cloud, and you can pick the right region for that public cloud. But the rules on top of that for ensuring that it's happening, that requires some higher level logic. We did actually at a tech field day, I think about a year ago, demonstrate some advanced technology that can do that can provide functions that monitor the location of the data and enforce rules on top of that. So that's available, I think, in one of the online repos.
So if I go to Scality's website, I can find a white paper on how Scality helps me with data governance, data protection, compliance.
I don't know that we have exactly that paper. We may have done something on GDPR, actually. We have. So this is Josh, right? I'll follow up. And
what you should do is get Ray to write it for you.
That's a good idea. Okay.
Yeah, it definitely sounds like a good white paper to write. I think a lot of the functionality that we have implemented, it's the identity access management functionality of AWS, really helps out with this, because we can do a lot of things like controlling what country you're accessing your data from, controlling, having really special rights and privileges associated with data. The kind of the nightmare of ACL management of traditional file systems is really can be very fine-grained with an object storage platform.
So I have another question, Brad. Yeah. A lot of the AI activity nowadays is moving out of the data center into the edge. So how does Scality fit into that framework? Is it more or less, taking the data from the edge and storing it someplace, or is it actually operating in these massive edge platforms that some of the environments seem to have?
That's one of the key drivers behind this Artesca launch, is the ability to have a technology that we can put where it makes sense. And I think one of the things we're definitely seeing is this need to have data stored safely at an edge, because you don't know for sure how long it will going to be there. And if there's really precious data in that, then being able to do things like run a Kubernetes cluster locally, do all kinds of work on that data, extract key events from the data, push that back to a central platform. So that's one of the key proposals of the Artesca platform, is being able to run it lights out in a remote site, and being able to replicate back to a center platform and have an elastic geometry of platform. The Scality ring requires at least 3 servers to run. And so we have the Artesca platform that can run from a single server all the way up to who knows how big, but that's certainly one of the drivers. And I think how big is the edge? That's a really good question. But
so while we're on this question, Kik, sorry, Brad, just to
go
jump in real fast. You mentioned the libraries, and I missed. Is that going to be something that's opened up to everyone, or was that for internal use at selective companies?
So
Libraries
I
for
think
nominees.
when I spoke of Gaia X, it's a very public initiative. The goal is that almost all the work that's going to be done there is going to be open source. But the genomics, we work with a number of companies doing genomics research. And these are things that I'm just explaining. These are things that they're trying to figure out is how can we create tools that allow you to request certain features in data sets, identify certain features on genomic sets, rather than shipping over 200 gigabytes of data times 1,000 people and say, see if you find what you need in here. So I think those algorithms are most likely going to be open sourced and shared between labs, and there's already a lot of open source tools out there. But the more the tools to talk the same language about gene sequences are available, the more the richness of the data, because that's kind of one of the problems today. I know a lot of companies we've talked to, the people that are doing for pay gene sequences of your pool, very often they just throw the data out because they can't keep it. I think in conclusion, if I see some characteristics, and these have really driven a lot of our work, characteristics of storage in this space, there's the idea that you have to be able to start small, but you have to be able to scale, and you don't know how large you have to scale to. And we've seen that in this space, and I think people are more and more starting big, but for many years, people were starting very small. And very often, AI/ML projects start as kind of a skunkworks thing, and they start with 10 or 20 terabytes of data, and then it grows, and if it's successful, it becomes massive. But having that ability to start small and scale, once you put a lot of work into a workflow, it's really painful if you have to change everything. So I think that scaling is really important. Being able to keep your data safe at a reasonable cost is so key. So many of the people that we were discussing with, their data sets are the value of their company. And some of the data, the older it gets, the more important it is. It kind of depends for each company what's the really most important thing. But we see this common trend in the data that people that are studying is very rarely. It's if you lose it, it's just gone forever. You can't make it up again because it's real world data. I think another thing that you can see really clearly, it's really important to be able to tag key events in the experience of in this giant pool of data having key events. And maybe you'll find more key events in the future, but if you find something, and this is one of the big problems in monitoring systems, that you do subsampling and you lose major events. And so being able to figure out how do you retain the key events without keeping everything is really important. Obviously, being able to support massive ingest of massive quantities of data. Filtering is clearly really important.
Hey, Brad.
Yeah.
So how does something like Scality support Kafka, messaging, logging, and those sorts of things? These things that are logging data at massive transaction rates and things of that nature.
So today, the tools that we're using, we've done our biggest ingest rates have been done with Splunk platforms, who are just pushing the petabyte a day platform is just literally writing data to a file system. We have systems doing several hundred terabytes that are writing to an object platform. So Kafka certainly could be used for something like that, but really, we're not doing anything particularly exotic. We don't have a special stream processing or something like that, where we're just writing massive quantities of data. And very often it's logs, sometimes it's images, different kinds of things.
Do you have any metrics on ingestion rate caps by scale, or just how fast can it go? Because I do have some needs for some really high ingestion rates. And they're bursty, so it's not by day; it's literally gigabytes per second kind of rates.
Yeah, I mean, I don't have hard numbers. We're very often doing 20 gigabytes a second kind of rates, so that's not quite HPC platform. We have a request going on for a customer that's doing over 100 gigabytes a second, and then you get into all kinds of exotic issues around networking and things like that. But our technology really wasn't imagined to do data rates which go beyond what the interface cards on computers, traditional computers can do. But the horizontal scalability of the platform has allowed us to run quite comfortably up into the 20 gigabytes a second range on a pool of very ordinary hardware.